was still a black box. And it's like a black box for many people. We don't know how it works. So that was where my interest. And then I thought, okay, let's do on GPS. But at the time in Japan, so there were no such universities that provide the education in GPS, because it was not subject to go into very deep, like a PhD or like that. So I couldn't do a PhD on that subject, but what I did was on the laser mapping. So it was a very new concept at the time to make a 3D data from the laser scanning. So that's, I think, very much, it's more on the physics side. So how you use all these optics and these things to make an image from this laser scanning. But slowly, the development of GPS started in Japan, and I shifted there and getting a lot busier in this thing. So today's my talk is more on the GNSS and less on the space weather, because I'm not the expert on space weather. I don't know much about it. But when I do GNSS training and lectures, there were many participants from the space weather as well. And I asked them, why do you attend my training? Because I don't know, I don't teach anything on space weather, but I do teach very detailed in GNSS with the signal design, analysis, and very detailed part we do. And they said that they would like to learn it, how GNSS works and how the signals looks like and how they can use this for their research. So that's where we got somehow the interacted. So today's talk, I would like to focus on how what is GNSS. We give a little bit brief introduction in the beginning. And then I want to know what type of space weather research is being done in Nepal. Maybe we have some time to discuss. And then I will also would like to explain what we are doing in terms of the GNSS resources in Nepal through the university or through the government here. And then we want to find out how we can collaborate or how we can go ahead from here. Okay. So these are the contents that I wrote here. So already given in my introduction by the Vice President of the NPS. But the order is, I changed the order because the more, I think I have more information for GNSS and the low-cost systems rather than other items, because other items, so we need to discuss today. So let me give you a little bit about GPS or GNSS. So normally we say GPS until the last maybe 10 years, but nowadays we call GNSS. That's acronym for Global Navigation Satellite System. And when we say GNSS, now it includes all these GPS, GLONASS, Galileo, Beidou, and QGIS. This is the Japanese satellite system, which is similar to GPS. It's also called Michibiki. And then we have the Indian system called Navig. Let me put the pointer here. Oh, you can't see the pointer, do you?
No, sir.
This is very strange. So I really don't know why this computer is not behaving well. Anyway, so, okay, let me just proceed. So we have so many systems called GPS, GLONASS, Galileo, Beidou, and QGIS. So these are the different types of systems from different countries. And all these were developed, like Galileo, Beidou, QG, and Navig. They are new systems and developed within the last 10 years, not very old. So still the satellites are being launched and they are providing many new signals as well. So in the space weather, I think normally you use this L1, E1, B1 signals. Okay. Now you can see the pointer, but there's a very large delay actually. I don't know why. So anyway, so you see the L1, E1, B1. So these are the signals that are quite commonly used for navigation and also for many space weather related researches. But also we have many other signals in the L2. These are the frequency bands, so the values are written here. In the L2, you can see the small text, so please see the PowerPoint later. Also, we have L5 frequency band. So there are so many new signals coming up in L6 as well. So L1, L2, L5, L6. Then we say this, we call this as a multi-frequency and the multi-satellite system. So once we have so many signals and so many frequencies, so you have more opportunities to compute different types of parameters that may be related with space weather or maybe timing or maybe the positioning related. So it gives more and more opportunities to do the signal analysis. But I don't know how it can benefit the space weather community, whether these more frequencies will provide you more outputs or better outputs. I don't know about this. So that's the reason I also want to learn how it can be used for space weather. And I'm already in contact with some people in the USA and Europe to know how we can benefit by using so many signals. If you count all these signals, I think there are more than 100 different types of signals. And this is the Japanese system. Okay, it's okay. It's quite long delay I see here. So this is the Japanese system called the QGSS. It was actually launched in 2010, the first satellite, but the service was declared as a reliable service to use for the positioning and navigation only in 2018. Because once we launch the satellite, so we need to verify all the signals are perfectly working, and you need to provide more than one satellite. So that takes a quite long time. So it took almost 8 years to make sure that everything is perfect. So it was declared operational in November 2018. So you see Prime Minister Abe, and also you heard the news that he was on death, I think already almost 2 weeks ago. So he was there, and also the lady who went to the space, so and other members from JAXA and the ministry. So they declare it's operational in 2018. Now we have a very good service from these satellites. There are now 4 satellites in this space. So I don't go all the details of this, so I will skip this slide. Okay. Okay, so please check these slides later. It's about the characteristics of QGSS. And then I have another slide. I already changed the slide, but you don't see, do you? Now you can see, I think. Okay, merits of QGSS.
It is changing, yes, slide is changing.
Okay. So I will skip these slides. And now you see the QGSS signals and PR and ID. In this slide, you see many different types of signals that we have coming from the different satellites. Okay, so I will also skip this slide, just a very brief introduction what this provides, the satellites. And this is about the satellite orbit constellations, how the satellites is moving around in the space. And this type of constellation has a benefit that you will see the satellite above your head in Japan, but in Nepal or other Asian countries, so this is a different scenario. Okay. So now we have this 4 constellation satellite in the middle, and in future by 2023 or 2024 we'll have 7 satellites. The rightmost the figure you see, then we'll have 7 satellites. So out of 7, the 3 will be geostationary, means that you will see the satellite at the same location all the time because they are stationary, or it means geosynchronous. And then you see the other 4, it's moving in a figure of 8. And here you see some special applications of the signals. And at the bottom of the list, you see SAS. This is called Signal Authentication Services. So this is not yet transmitted. This will be broadcasted from next year probably, and this is where now I am doing. So I am doing a sort of a design of the new signal to do we say the authentication services. This is for very secure and safetiness of the signal, so that you cannot. We call the word spoofed. This is to spoofing means that you can actually falsify the location data that's coming from the satellite by using some sort of a false signal. And this can be done very easily nowadays. So that's a very threatening part to the GPS community. And for example, now I'm in Tokyo, and if I do the search in the Google, like in my mobile, to know where am I. So if you do the local search in your Google, the mobile phone use the GPS receiver inside the phone, and it will compute the position data from the GPS satellite and tell you that you are in Tokyo. But what I can do is we can falsify this position data to spoof or to falsify the satellite signal itself by broadcasting some other imitating signal or the false signal by using some radio device. Then I can show that I am not in Tokyo, but I'm in some other place like Kathmandu or Bangkok or like things like that. So that's a very, very dangerous things that can be done. So in order to protect from such type of spoofing, or like you can say sort of a hijacking of the location data, or attacking the receiver itself, or attacking the satellite. So in order to stop that, we are now designing the new signal that's called the authentication service. So that's my main development work here, and we'll implement this in the satellite and broadcast from next year. That will be a new service. Okay. So it has nothing to do with the space weather, but this is a completely different service. And let me go to the space weather slide. So this is the launch schedule. I will just skip this and go to the space weather. This is our main discussion, part of discussion. So I took this slide from the homepage of, I think you saw this slide many times by the presenters from Europe or ITCP. And I think you saw this when you had this workshop in Oslo, Amri Science College, a few years back. Some people came from Europe. During that time also, I had some discussions with the people from Europe, how is Nepal and how to travel and what are the things they need to prepare. So we had some talk here. And I think you saw this, and this is now showing you how the space weather, or like the ionization, or this type of solar flare or plasma bubble, how they affect the radio signals. Not only GPS, any communication satellites or the radio signals will be affected. If that happens, then this may disrupt the communication. The satellites may not work, or in the case of GNSS, we will have a very large error, and that gives us a very large positioning error. So it's not that good, and it may affect the like a communication in the aviation, like the aircraft, and also the aircrafts. They would like to avoid the highly ionized route, okay? Because they don't want to lose the communication with the satellites or other communication links for the safetiness. So there are so many factors that affect, but what we do in GNSS is that once you have such type of some disturbance in the space weather, then our signal is disturbed. So that's a problem. But by looking at the disturbed signal, we can compute how much this is disturbed, how much this is changed, delayed, or some other problems in the noise coming in the receiver. Then by measuring those noise or the disturbances factors, we can reverse compute, okay, how much ionization is there in the space. So that's what we do. And we use those factors to improve the position value in the receiver. Now, I don't know, when I say space weather, I don't know what does it mean actually in terms of the GNSS studies. So I just I'm asking this. So when we say GNSS for space weather, what can we do in GNSS? And to what level? So this is my question to space weather community in the Europe. Now we are discussing Europe and USA and probably in Nepal as well, those who are using GNSS. So when we say GNSS for space weather, so what does it mean and how we can use and for what? For example, I put here some ionospheric related TEC or ROTI, rate of change of this TEC index. So we can compute the TEC, total electron content, to find out how much the electron contents is there in this space and how this is changing, the rate of change. That is one of the applications very widely used by the people in the physics using the GNSS. And then we have another terminology called the scintillation. So when you have this type of very high electron content, then we can measure the scintillation, how it affects. And there are some index called the S4 or 5 values. The S4 is using the quote phase, and we say the quote phase and the carrier phase in GNSS. So we can compute these some parameters for scintillation as well. And then the tropospheric related, I don't think this troposphere belongs to the space weather because the altitude is not that high. So, but the tropospheric is another widely used parameter estimated using GNSS for the estimation of the precipitable water vapor. And this is very important. If we can do well, we can predict heavy rainfall in advance. So this is what the researchers are saying. But I myself don't know how much it is, to what level it is possible. It's a part of a research. So if this is possible, then we can predict the heavy rainfall or the sudden rainfall at some place by observing the GNSS data. But to do that, you need a lots of stations at certain, I don't know, probably every tens of kilometers area. And then radio occultation is in the space. This is like you have a GPS satellite, but that satellite may be blocked by the other, like the Earth. So, but even if it is, when it is like a blocked by the Earth, you still can get some signal at the backside of the Earth, because when the satellite moves at the edge of the Earth, if this electron content is very high, then the radio wave is a little bit reflected or diffracted, not reflected, it's diffracted. So when it's diffracted, so although you can't see in the direct line of sight, when the ray is diffracted a little bit by some angle, you can see the signal. And that's very beneficial now in some applications to measure the electron contents around the surface of the Earth. And that also gives another opportunity to do a very challenging navigation, like a moon navigation or this type of celestial or space-based navigation, to navigate the space station in the space or something like that. Yeah. So this is another very interesting topics to do the radio occultation here. That's very important as well. But after all, okay, we do lots of ionospheric scintillation, all these type of very high level research. But the question is, okay, how can we use for the practical applications? So what's the benefit of this doing? How can we use this for our daily life? For example, aircrafts, they use this ionospheric data to guide or to avoid the highly ionized air route. So probably one of the users is the air route, like aviation sector. Then also like a prediction of the heavy rainfall, maybe then weather forecast or weather news. In Japan, there's a company called Weather News, so they use this type of data. And maybe prediction of huge earthquake. I don't know whether this is possible or not, but we heard that when before the huge earthquake comes, the space weather, it's disturbed by the high ionization or something like there. So something changes in the space, basically the ionospheric level. So if we can detect that in near real time, or then probably we can also predict such type of very huge earthquake. And then of course we can also predict the disruption of the communication services. So happens actually. Actually, you have heard the news that in this year, the SpaceX launched, I don't know how many tens of hundreds, I think 100 something like of satellites, and tens of those, several tens of those satellites were all damaged due to this space weather. Some impact on that. So this type of things can be avoided if we know the situation in this space in advance, but it's very, very difficult. And so the question is, who will be the users? Okay, aviation sector, weather, telecom, or satellite companies and all, and how we can help them to do all this type of prediction and they, get the results. And on the other hand, also we need to do some lobbying to policy and decision makers. Like if we want to do this in Nepal, for example, okay, we want to do scintillation monitoring, observation, or ionospheric or tropospheric at a large scale, a smaller grid, then we need probably, I don't know, maybe say 20 or 30 stations all over Nepal. And that's a lot of money because this type of space weather receivers, the special receivers, are extremely expensive. As I think it costs at least $30,000 for one unit. And then on top of that, you need the operation and maintenance. So $30,000 is the receiver cost with the antenna and all the infra. And then you need the additional cost. So who will pay for that? And if you need like a 20 of that, that's a huge money. So we need to first let the policy and decision makers know that why this is important, who can benefit, and how this can be done. So that's not a very easy task, but at least we need to let them know why this is important. And these are some snapshots I took from Japan. So they provide the near real-time TC. You can check this in the website and see how they provide the service, what level of service. Okay, so let me skip. Now I go to a very important topic, to low-cost receiver system, because this is what we want to do for the space weather community, because those type of high-end receivers for space weather is quite expensive. It costs almost $20,000-$30,000, and that's very difficult to acquire by universities, because universities around the world, they don't have that much of budget. So if you need to buy a $10,000 receiver, that's too expensive for the universities. Even if you buy just one unit, and you can't do much with one unit. So how can we do lots of research, benefit more people, more researchers, students? How can the students get access to the receiver and so on? So then I propose, why not to try or develop the low-cost receiver system? Because I am involved in developing low-cost receiver system for the high accuracy positioning system. Even high accuracy positioning receiver, they cost more than $10,000. But $10,000 is still too much or too expensive for the universities, even in Japan. So we can't buy that one. But when we did some research 5-6 years ago, we found that the receivers already in the market, there are some modules, not in the packaged one, but there's some chips and this type of components. And if we can combine those type of components, and if we can make some software, we can have a low-cost receiver system. This is what we did. And we already have this type of things already developed. And now we are promoting this type of low-cost systems in Asian universities. And we have a very good result. And this can give you accuracy of about 10, 20, or 30 centimeter without any problem. We have already logged the data and all. Now we want to see whether this type of receiver can also be used for space weather. But space weather has a very strict requirement at very high level of raw data output, which is a little bit difficult for the low-cost receivers. They can't output that level of data. Raw data. So, but still we want to see to what level we can do it and what type of output we can provide. Like if we can provide only TC, okay, at least for the TC computation, we can use low cost, but S4 and the phi index may be rather difficult, but we want to explore. So this is the main point of today's talk as well. how we can use the low-cost receiver for the space weather community, so that you can have maybe buy 20, 30, or 50 of these units, because the cost is very low. Maybe within $300, you can buy one unit. Yeah. And this is how it looks like. So actually, it's very simple. But we do the customize for you, or we can provide the data how to customize. So people with some hardware and software knowledge, I think they can do this. So on the left side, you can see some chips. We have been trying this type of chips, and then we need to do some hardware system integration. But this, we already have this type of system already. So it's not, you don't have to do from the scratch. So you can get the device as a sample device, and then you can buy the products in the market already available. And what you have to do is probably you can just buy those components and then just attach them by either by cables or by some connectors and put in the box, and that's all, and it works. And then you need the software. So we need to provide you the software. Okay. So these are the things now we are discussing with the international community. We provide the hardware for the GNSS, low-cost GNSS, and the space physics or the space weather community, you provide us the software. And then you provide the know-how, how to process the data, GNSS data. We provide the hardware, you provide the software, and you provide your know-how. And then we'll make an integrated system and develop a low-cost receiver system for space weather and deploy it around the world, so that the people in Africa, Asia, Latin America, they can also benefit, and they can do research at the very core level, at a very low level on their own, and they don't have to depend all the time on the donors to get those 20, 30,000 expensive, extremely expensive receivers. Okay. So this is the target to develop low-cost systems on our side. And this slide now shows what we did and when we did this. So you see on the left side, actually we started this in December 2016. So we make this demo when we had the UN Nepal GNSS seminar in Kathmandu. So this board is very crude. We don't have any box. So it's very, just at the prototype and the idea level. Then from 2016, when we came to 2020, then we have a very perfect system. So within 3 or 4 years, we did a lot of changes on that. And now you see on the right side, at the bottom right, you see the GNSS and Madoka receiver. So this is a very small box, and that cost is about $300. And you can find this type of receiver in the market, but in a larger size, that will cost you around $15,000 to $20,000. So we were able to reduce the cost from $15,000 to $20,000 to $300, and it still provides the same level of output. You can see here with the Raspberry Pi, that's a $50 computer connected to this receiver, and you will get accuracy of about 20 centimeters. This is for the positioning and for surveying mapping. But you can also use this for space weather. So we want to explore this type of device, how we can use this for space weather. Now we are discussing, and we have a project team, international project team, to explore this, how this can be used. And this, now we also provide some sample devices to the universities with collaboration with us. And this includes our receiver and the Raspberry Pi computer with a touch screen, and you get the antenna, receiver, touch screen, Raspberry Pi, and you just connect with the cable. So you see this on the right side, you see the black box, and then you just connect the cable, and we provide the software for positioning. But for space weather, we don't have anything at the moment, no software. Probably our researchers from the space weather, they can do that. And also we also have this Android version, so you can also connect this type of receiver to your mobile phone. So this is how we can make the system very low cost. So if you can use your Android mobile phone, because it has a GPS receiver for your space weather studies, so that's I think the least expensive tool. You just go out, put your phone on, and log the data, and then you compute the scintillation, or not the scintillation, I don't think it's possible, but at least TEC, maybe it's possible. Okay, so you can just use your Android mobile phone. So this is another opportunity or another possibility that we need to explore. And this one is actually, I'm just showing you how the GPS receiver works inside, what type of circuit it has. But we also have a concept of the software defined radio, or SDR. You see on the bottom, SDR, software defined. So you just buy a front end that converts the radio signal from high frequency to the low frequency. We call the IF, intermediate frequency. And then you convert to digital. So this device just converts from the analog to digital signal. And then you process the digital signal in your computer by writing your own program. Okay, so this is what we call the software defined radio and you can use this for GNSS data processing or space weather data processing and all. There are lots of possibilities here. But what we need is the software to do this. And probably some of us may have this type of software already available, but we are also exploring on this and see how, to what extent we can do this. And here you can see the raw data output. So this raw data output means we will now output all the necessary raw data that is required for space weather. Now, we have a request to the space weather community, what type of data, what type of GPS data you need. So please tell us, then we'll output this data and then you can use it. Okay. So because we don't know what type of data you need. So we need to ask you what type of data you need, then we can output those data. So if you look at the GPS data, the actual data, the signal inside the receiver, it looks like this. So you see these graphs on the top. You have the time-based plot as it enters into the antenna. And then in the middle top, you see the power spectrum or the FFT of this time signal, and then histogram, how the signals are distributed. But on the right, the top, the tracking output IonQ channel. So this data is necessary to compute the space weather related information. But we don't know to what level, what frequency, and what sampling rate are required. We need to explore, we need to talk with the people in the space weather community. But I think this is what you need. So if we output, probably you can do what you need to do. And these are some of the outputs that the commercial, the high-end receivers output provide as an output from the receiver. But unfortunately, this type of receiver is quite expensive. So this is the output from the Septentrion Polar RX5S receiver that's especially designed for scintillation. It's a very special receiver, but I think the cost is $30,000, something like that, dollar or euros. So it's quite expensive, but it's quite good that it outputs all the data you need: S4 index, phi index, SI index, and TEC, and so many other things. But the cost is too high. So I asked them whether they can reduce the price for the universities, but it seems to be quite difficult because there's not much demand of this type of receiver as well. So the demand is very low. And now, ultimately, we want to focus on these two types of receivers. One is from the company called uBlocks. Another one is from the company Septentrion. And this is, their name is Mosaic, the receiver, the module name is Mosaic. Now we have both of these, and we have developed the low-cost receiver for the positioning purpose. Mosaic is a little bit expensive, but it has more features, whereas F9P is cheaper, but it has a little bit limited output. I don't know whether it can fulfill the requirements for the space weather, but we need to see whether it can be done. Now, this is what we are going to explore in the next maybe 1 year. And there are also possibilities to use the mobile phones to log the data. Actually, if some of you in the space weather community for GNSS, if you have attended this training conducted by ICTP in May 2022, they have a very nice session on this. So please download data from their website. It's very useful, very good information. Actually, I myself joined this because I'm also new to space weather, and I found this is quite interesting and quite good and very, very nice. So it's not possible at this moment to use the mobile phone, but in near future, I suppose that we can also use the Android mobile phone. And I'm actually using this to do my positioning or this location type of analysis. It's quite good, extremely good actually. But for space weather, probably there are some limitations. And then I will skip. Now, currently what we are doing is that we have established a project team under ICG. ICG is the International Community on GNSS. This is within the UNOSA, United Nations Office for Outer Space Agency. And there we have ICG, and under ICG, we have a working group called C. This working group C is for technology promotion or capacity building. That's what they say. And in this capacity building working group, then I propose to have a project team to explore the possibilities of space weather using the low-cost GNSS receiver systems. Now, what we are going to do is we'll try different types of low-cost receiver. You see in the receiver block, I put some modules here. Then we need some software. I think these are some of the software that I was given information just last week. FLIR or Gopi or Niquick for an Artically. So this is software from Japan. And then probably, we don't know whether we can get this type of output. These outputs are from the NICT, very high-end receivers. And in Japan, we have 1,300 stations, GNSS stations. So we can have a very nice, this type of near real-time output. But if we have one or two, so it's rather difficult. But anyway, the most important part is software here. So now we are discussing what type of software we can use, who has this software, who can provide the know-how, who can help us to do the data analysis. So if some of you are interested to join this our team, so you are most welcome, and you can help us by doing some analysis of GNSS data for different types of TEC or S4 index computation and all. And actually, so we are discussing this last week on the 14th of July with some professors from Europe and USA, and you already probably know that Professor Patricia. So we were supposed to have a Zoom meeting, but she did not come, and we sent the email, and then after some time, her son sent us the reply that she passed away a few hours back. So unfortunately, we could not do much talk on that day. So we'll have a meeting next week to discuss about this software. So we are now exploring in to see how we can do this. So probably we also need help from your side. And so now I have only a few slides now, and these are some of the stations that we have in Nepal. We don't have much, so just two actually. So we have one station at Nagarkot, and this was established, I think, around 2010 or like that, 10 or 11. I don't remember the exact date, but yes, quite long time ago. I think 12, not 10. Sorry. So we have this very high-end GNSS receiver there. It's from Trimble Net R9, so it can receive signals from many satellites. And also we have one at the WRC Pokhara. So this is not from our university, but we work together, we help them. And what we propose them is that why don't you apply the funding from the government of Nepal? And they said it's not possible. Then I said, why? So we had lots of discussions, and then said, okay, they said that there's a UGC, University Grant Commission, and they provide some funding. Then I asked them to apply with a very new concept of establishing this type of base station. So if we don't get, then we'll provide from the University of Tokyo. If you get, then we don't have to provide, or we provide an extra set for you. So, but they applied, I think it's 2 years ago, they applied and they got it. Okay. So now they have this, you see the antenna here on the rooftop, under this tripod. So this antenna, and this is a very nice and a very latest receiver. It can receive all satellites, all signals with a full spec. It's much better than the survey department Narcot receiver. So I think this receiver at Pokhara is the most highly specification, the highest specification receiver in Nepal, because I requested the manufacturer to put all the signals that can be tracked here, because this is for the university research purpose. So they were also very generous to do that. So we have a very fully spec. So if you want to do very detailed analysis, very different type of data analysis, so you can use this data from Nagarkot as well as WRC. I recommend the data from WRC. That's much better. And also this provides lots of very raw data that probably needed for space weather. And also we have lots of collaboration with different Asian universities or universities in Asia. So these are some of the lists here. We have collaboration with Indonesia, Laos, Malaysia, Myanmar, Thailand, Philippines, Vietnam, and also Mozambique. Rwanda is not listed here, but yes, and Singapore and Australia. So all university to university collaboration. Of course, I have collaboration with WRC in Pokhara as well, and sometimes we talk with the IOE, Pulso, sometimes Kathmandu University. But what I did is that we set up all the infra at the WRC Pokhara, and we want to make that as a central point for sharing the resources, because these type of resources are too expensive. It's not possible to distribute the resources to several universities. And also for Asian university, we are doing the same for these countries. Okay. And I just did some website search. So GNS, what type of research are being done in Nepal? And also I got some information from Dr. Christine from France. So she is very closely related, I think, Dr. Chapagai. Also some of his researchers and students doing the PhD. And on the right, you see the workshop you had at OSCO. I think probably you know more than I do. And I do need input from your side, from NPS, to tell me what type of resources in there, and we can help you to provide the data that's necessary, or we can add one more topic of the research using the low cost to see how we can use the low cost receiver system. Okay, so this is my intention to do this talk program as well. So how we can help to do the research using your own receiver. So far you are getting the data from UNAVCO and all these stations in Nepal, but I don't think they are working up to the level that should be. And these receivers, I think, except the 2 or 3, they are quite old, L1, L2 only probably. And now you have the new signals, L1, L2, L6, L5, and the Beidou, the Indian satellites there. So many new satellites. And I don't think UNAVCO, the receivers, they can receive all those because they were installed many years ago. Okay. So to summarize, so there are so many things written in the text. So what I want to request you is now the last one, need to have a close collaboration between GNS community and space weather. And the question is, how can we help each other? So what we need to do, what we should do, whether we should provide, how we should provide the data, if you want the data, what type of data, and how we can share the resources among the communities. Maybe in Asia, Japan, and also we have from Europe. And also now in the project team, in the ICG, we are also discussing how to share these resources, which are all scattered around the world. And there are different types of resources, software, hardware, and know-hows, or people resources, human resources. Maybe we go somewhere to give the training, or you go, or you come somewhere to learn more things. So these are all the things maybe we need to discuss from now. And today is like just a kickoff talk or meeting for me. So please let me know what I can do or what we can do and what type of things we should do. Thank you very much.
Thank you, Dr. Manandhar. Now, we have discussion time. In chat, there is few questions. I want to read it from Darvindra Pandit. He asked, is there any chances of radio interference in space due to a lot of signals? Dr. Manandhar.
No, it's not, because all these radio signals that are being broadcasted from the satellites, they have to follow the regulation by ITU. Okay. So the power, the radio signal, all the radio or other communication signal power, it's regulated by ITU, International Telecom Union, and you cannot simply transmit high power as you like. So it's all regulated. So they don't interfere each other. But definitely it will increase some noise floor. That's why you have to choose the different types of signal band and the signal type or the signal modulation. So in this slide, you saw already, okay, for example, this type of different types of signals in my introduction slide, slide number 3. So you see different types of signal, the image. So this is the reason why the signals are designed like that, to avoid the interference to each other. Yeah. What's the another question?
Another question is from Pushtuva Regmi. She wants to ask how micrometeoroids affect space weather.
Oh, sorry, I have no answer for this. I don't know this.
Yeah, it's quite interesting in perspectives of physics. I think so.
Yeah.
Scientific.
I'm not good in physics. Sorry.
Okay. Is there any other questions? You can ask directly or raise in hand.
Yes, sir.
Okay, Basudev Gimire, please.
Yes, sir. Thank you, sir, for a very nice and very informative information for you share with us. And I'm doing this. I'm working in these types of GNSS and GPS lights data. And then I want to know what is the difference between this data taken from the UNESCO and then data what got from the WR Pokhara, like this number 2 Pokhara. Is there any difference?
No, because data are the same, okay? Because it's coming from the same satellite. But what I was saying is that UNESCO stations in Nepal, I think they were installed quite long time ago. And those receivers, they can receive L1 and L2 signals from GPS and GLONASS. Okay. Now, I don't know what type of data you are using. If you are okay only with GPS, L1 and L2, then UNESCO data is more than enough. That's perfect. But if you want to challenge as a researcher with a new signal, like L5 signal, L6 signal, because you see the ionosphere, the effect of ionosphere on the radio signal is different for different frequencies. Okay? So it's a completely different effect on L1 and L2 and L5 and L6. So as the frequency differs, the impact, its effect on the signal is completely different. So what I'm saying is that if you use more signal or more frequencies, probably you can do something new or something different from what others are doing. Now I see the research and almost everyone used the L1 and L2. Now my question is why you don't use L5? Why you don't use L6? Okay, and why don't you use other satellites? So by using different types of satellites, using different types of signals, using different frequencies, probably you get much better data. I don't know, it's better or worse, but I think we need to explore.
Thank you, sir. Thank you so much.
Is there any other questions? Here again from Dharvendra Pandit. Why specific band of frequency are used only in GNSS study?
Okay, so one important part is to avoid the interference. Okay. Another very important part is for high accuracy. And if we use a single frequency, for example, if we use only L1, what will happen is that because the ionospheric effect is always there, there's a electron contents in the space, and that is affecting the signal all the time. We can't avoid. But if we know how much electron is there, we can compensate in our positioning algorithm to remove those effects. So you can get a very high accuracy of centimeter level. But if you use only L1, you really don't know how much is there. It's very difficult. But if you use L1 and L2, the effect on L1 and the effect on L2 is completely different. Now, by looking at L1 and L2, then it's much easier to compute how much electron content is there. Okay. For example, so in a layman word, what I can say is, if the L1 impact on L1 is a positive, the impact on L2 is negative. Okay. That means if one parameter is increasing, another parameter is decreasing. So if we know if we are observing two frequencies together, then we know which one is increasing and which one is decreasing. Okay. So it will help us to compute the correct electron content, and then we can remove the impact on the signal to have a very high accuracy. So if we don't have, then this TEC or the electron, I don't say TEC, but the ionospheric has an impact of about accuracy. In terms of accuracy, it's quite high. It's about 3 to 5 or 6, 7 meters of impact. Okay. So you will get that much of error in the positioning. But if you can remove those errors, then your accuracy improves by 3 to 5 meters.
Okay.
That's why we need a different frequencies.
Okay, Rudra sir, could you please put your query?
Very nice talk, Dinesh sir. Thank you so much. I have a very layman question. Like, what is space weather? Like, how is it related to the like this weather, day-to-day weather, like modeling? Like, so are they connected, or they are same thing, or they are different things?
That's also a question from me. So that's what I want to know.
Thank you.
So maybe I would like to have an answer of this question from some of our experts in the space weather who are, yes, doing GNSS, if there's some participants today.
Okay.
And
Okay,
in our
Narayan sir.
team, I'm also asking to give a definition. Yes.
Can I take a few minutes?
Yeah.
Yes, please.
Okay.
You are the expert.
Okay. Thank you so much, Dr. Manandhar, for your very informative and nice presentation. Thank you so much. And actually, we did have conversation around 1 month back or 2 months back.
Maybe 2 months. Yes.
Yeah, great. Actually, what you have mentioned here, that some of the software that can be used for data derivation, that is Floor, Gobi, and NetQuick. These all software we have been using for the UNAPGO data analysis. And our group, just a few, I think the Dravindra and Basu are also here. And they are working on this space weather and as well as this UNAPGO GPS GNSS data. And we have many papers regarding to this data. We are working extensively in the TEC data from Nepal. even climatological study also. And as I think someone asked the question, what is the difference between GNSS data and this UNAVCO data? Actually, UNAVCO data gives only the data from the GPS receiver that is deployed by US. But from GNSS, it is important that we can get the continuous data from there, because the GNSS can receive the data from different satellite when it is passing through this region. Therefore, the GNSS data will be definitely important to continuously monitoring the TEC data from that region. And regarding to the question to the space weather, actually the space weather and terrestrial weather, they are not correlated to each other. Space weather is actually influenced by the solar activity, such as solar wind, solar flare, coronal mass ejection, that causes to the change in the magnetic field in the upper atmosphere, and that also change in the ionospheric region in the upper part of the ionosphere. That causes the effect on the space. That is known as space weather. And space weather, actually, to know about the space weather, we have to monitor the TEC data, ionospheric data. There may be other types of instrument that may be some optical imaging data, and there are many ways that can be used to monitor the ionosphere. And we continuously monitor the TEC data from the upper part of the ionosphere, and at the same time we'll see the solar activity, that is how the geomagnetic storm over there, and then we can find that whether there is effect of the space weather is there or not. Geomagnetic storm effect is not, or is there or not. That means space weather is mainly concerned, influenced by the solar activity, geomagnetic storms. That can be predicted. Space weather also can be predicted by continuously monitoring the activity coming from the sun, that is geomagnetic storms. And actually, we are looking for the collaborative work with using some of the low-cost GNSS receiver. But since we have already GPS receiver here, and we have data, as you said, about TC and even scintillation data. Basuji, are you there?
Yes, sir, I'm here.
Yeah,
Yes,
actually, you are also using the scintillation data from the UNAVCO, from GPS, isn't it?
yes, sir. There is Gopi software will provide the scintillation data for 5-minute resolution.
Yes.
And we are using that data, ROTI and Expo index.
Okay, as far actually, Dr. Manandhar mentioned that we can predict the earthquake from this TC data, but it is not still some dilemma whether it can be predicted or not. But the important things is that we need the continuous data from the single station that works from the GNSS. So that will be the important from GNSS rather than GPS. From GPS, will not get the wide range of the time of the data, but from GNSS we can get that one. And I think we will work with WRC also, so that we can compare with the GPS TC with the GNSS data obtained from there. Thank you so much for your presentation, and a nice presentation. Thank you.
Thank you, Narayan sir.
Okay, so
ma'am.
So the screen you see here is actually the real time. I'm accessing the receiver in real time. So you are seeing the data coming to WRC. So it's a very high-end receiver, very detailed raw data you can get it. So if you want to do some space related like a TEC, or maybe you can also try with this data.
Yeah, it is power, yes, and I think they have not used yet the software to convert in TEC data yet. Probably.
No, this is because we do this for the positioning, not
Okay.
for the space weather,
Okay.
because we don't know how to do this. But we can provide raw data that you need, and then teach us how to do this. Then we'll try.
Okay, sounds
But this receiver is a quite high end, quite expensive. And actually, we don't want this receiver to be used for space weather because it doesn't help us to promote the technology. And I have also provided the smaller module of the similar type, the low cost, that's also available at the WRC. They have now very different types of, several different types of receivers. $100 receiver, $300 receiver, $500 receiver, and this is maybe if you buy in the open market, it will cost you around $30,000. Okay. So many different types of receivers we have in Nepal now. So you can play around with the receivers, you can log the data, you can compare the data, and then this will give you a completely different type of research output as well.
Okay, thank you, Dr. Manandhar. Now it's time to ma'am. Ma'am, could you please put remarks and close the session?
Okay. Thank you, Dr. Dinesh. A very nice and informative talk. As Narayan sir told you that we can collaborate with GPS and GNS, but I have no much idea on the space weather and such things. But how can we help you? How can we collaborate? You can consult with Dr. Narayan Chapagai. He's also here in the Nepal Physical Society. So we can continue our research of this type so that our people will benefit from your research. We definitely hope that. And thank you very much once again from the Nepal Physical Society. So with that note, I would like to conclude. If you any participants, if have any questions, you can contact Dr. Manandhar at any time in his email. We can provide you. If you want to contact him, we can provide you the email address and many other things. So I think we have to conclude. And with that note, so I'll say goodbye, good night, or good afternoon somewhere in America. Okay, so let's clap and give a big hand to Dr. Narayan once again.
Okay, thank you very much. So my pleasure to have this talk program in the very prestigious, I think, this NPS. I found lots of activities. So it's, I think, very nice to have this type of interaction. So let's see what we can do. And if some researchers, they need to access the data, just let me know. We'll create an account so that you can access. For WRC, I can do very easily because I manage, I don't control, sorry. We do the manage, and what I'm saying at WRC is that let it be a sort of a focal point for the researchers.
Yes.
Okay. So we don't want to restrict the data. But for the Nagarkot, it's owned by the survey department, but we have access right there. Also, JAXA, we have access there, and we are going to connect that network to our global Japanese network as well. So, of course, you will not get the direct access from the SD survey department, but you will get access through our global network. So you can also get the data from Nagarkot, you can get the data from WRC, and we have some other stations in the eastern part that were established by some other companies. So they are also providing the data. And I recommend to use the data from the latest receivers. That gives you much better output, I think.
Exactly. Yes.
Yeah.
In Nagarkot also there is GPS or GNSS.
No, it's a complete, very advanced GNSS receiver. It can receive all the satellites, but not all the signals, but all the satellites. GPS, GLONASS, Galileo, Beidou, and all. But not Indian satellite because it was installed 10 years ago. Yeah.
Yes.
Because Indian satellite was very recent.
Yes, this is very good news. Dr. Harishankar Malik, you can post in our website also, because Dinesh Manandhar is here to help us using the data he's providing us. And the satellite is here in Nagarkot and Pokhara as well, no? He said. So we can explore our research activity to our society. Okay, thank you. again.
Pokhara data, you can get immediate access anytime. Just send the email.
Okay.
Nordcode data, you have to wait because they are doing the system update now. Maybe about a month, but Pokhara anytime is available.
Okay, that's good news.
Thank
Okay,
you,
then
everyone,
yes.
for being with us for this time. And this recording will be available very soon on our webpage. Okay, thank you. Good night, everyone.
Thank you very much, Dinesh. Okay, we'll see you.
Thank you.
In touch.
Thank
Keep in
you.
touch. Okay.
Thank you.
Thank you,
Bye-bye.
sir.
Good night.
Thanks.
Good night.
Night. So I'll leave now.